Hello, friends. Welcome to Science Talk. I am your host and resident oceanographer, Jim Massa. I want to discuss with you a paper that was published the 26th of April of 2022 in Geophysical Research Letters. And the title is, as you see, Future Amplification of Sea Surface Temperature Seasonality Due to Enhanced Ocean Stratification. Okay, now this paper is quite technical. There's a lot of mathematics in here, although the mathematics is, be honest, is really straightforward. It's not difficult, but it's involved. Um, what I'm going to do is I'm going to discuss the abstract with you. I'm going to discuss the figures that, in my opinion, best sum up this research here, and then some other aspects in the discussion and conclusions that the authors write about. I will, of course, leave the URL in the comments section for those who are so inclined to look at this paper in greater detail, and you can do so at your convenience. So, in many regions, the projected future sea surface temperature, SST, response to greenhouse warming is larger in summer than in winter. What causes this amplification of the sea surface temperature seasonal cycle has remained unclear. To determine robustness of the projected seasonal cycle intensification and ascertain underlying physical mechanisms, we analyze a suite of historical and greenhouse warming simulations conducted with 13 coupled general circulation models in the Coupled Model Intercomparison Project Phase 5. In the representative concentration pathway 8.5 scenario, the amplitude of SST seasonal cycle and the amplitude. Well, this is important. We want to, what do you meant by amplitude? It is defined as the difference between the climatological maximum and minimum temperature. And according to their work here, it increases by 30 plus or minus 20% on average by the end of the 21st century. Now, that's a pretty big error. So obviously, the model needs some working, but putting that aside, the implications of this work is very telling. Analysis of a simplified mixed layer heat budget demonstrates that the amplification can be attributed to the increasing upper ocean stratification and hence shoaling of the annual mean mixed layer. This is very important. You've heard me discuss with you how many times how the oceans are stratifying. Well, we're increasing the upper stratification, shoaling of the annual mixed layer. That means it's getting shallower. Just like ocean acidification is causing the CCD, where the lysocline occurs especially, to be getting shallower and shallower. Well, we're now seeing the mixed layer depth getting shallower and shallower. And the projected intensification of SST seasonality may have important implications for future changes in marine ecosystems. Now, before we move on to the key points, to determine robustness basically means how good do the models work. This is basically what it is. And now, when they talk about the coupled model intercomparison project phase, the representative concentration pathway. Okay, we're getting into the world of the IPCC. The IPCC has a number of different scenarios. 8.5 is basically worst case. And to be quite blunt, if a researcher is not considering the 8.5 situation, I'm really not going to look at the paper. because 8.5 is actually is best fitting the current data that we have. In other words, 8.5 is the exponentiating scenario, and that's what's happening. You're going to see it's like 3.0, 4 point, what have you, which tends to be linear. No, no. 8.5 is what the data is telling us is happening. Okay, let's look at the key points. Under the high greenhouse gas emission scenario, the seasonal amplitude of sea surface temperature is projected to increase by the 30 plus minus 20% by the end of the century. The intensification of sea surface temperature seasonality is largely due to the shoaling of the annual mean mixed layer depth. The advection term explains about 10 to 40% of the change in SST seasonality depending on the region. And as we'll see in the text, where they found the greatest changes was pretty much in the North Pacific, North Atlantic, Southern Indian Ocean, and then into the even parts of the Northern Southern Ocean. So, advection is basically movement of water. When water moves from point A to point B, you are advecting it. That's all advection means. And now the plain language summary. One of the robust projected climate changes in response to global warming is the amplification of seasonal cycle of SST, with larger warming occurring in summer than in winter. Well, it kind of makes sense. You got more direct sun energy impacting the water, especially in what I just mentioned: North Atlantic, North Pacific, South Indian Oceans. And they investigate the mechanisms. We show that for the high greenhouse gas emission scenario, which is the one best suited to the data. The amplitude of SST seasonality increases over the next 80 years by 30 plus or minus 20% globally. Overall, mean ocean warming increases the upper ocean stratification, which leads to a shoaling of the mixed layer. Let me highlight that. Overall, mean ocean warming increases the upper ocean stratification, which leads to a shoaling of the mixed layer. Now, they go on to state that this implies that climatological air sea heat fluxes impact a smaller ocean volume, which then leads to an increased sea surface temperature response. Okay, what this means, and they don't state it, but it's implied that thermal hailing flow is slowing, if not stopped, so the sequestration of the heat doesn't go as deep as before. Now, you've heard me say that about 68% of the heat energy absorption has been in the upper 5 to 700 meters. They're now basically saying that most of that heating is going to take place even in a even smaller, shorter, not as deep layer in the ocean. In other words, that heat may not even get down to 700 meters. It might be shallower. So you really concentrating that heat in the upper, couple hundred meters. So that does intensify the stratification. And I'll explain later on, what's happening with the mixed layer depth. The increased temperature seasonality could further impact plankton phenology and the climatology of upper ocean CO2. Okay? And they talk about other heat budgets playing a secondary role. Okay. Phenology is the science that studies the timing of things in nature. When do the trees bloom? When do insects larvae hatch? When do birds migrate? And they try to time when the eggs hatch with the insects hatching so that they can grab the insects and feed the chicks. That's what the science of phenology is. So basically, if you have these really warm in the upper ocean, in a photic zone. It could impact when phytoplankton bloom, impact when they start photosynthesizing, impact when they stop photosynthesizing. And of course, CO2, the acidification going on, the shoaling of the CCD slash lysocline, uh, organisms that need the calcite basically, okay, because the CO2 combines with water to form carbonic acid. Organisms that need the calcite may not be able to make their shells, their tests, and they are increased at risk of increased mortality. And another problem is if it impacts plankton, well, you're going to get decreased oxygen levels, and not to forget the fact that warmer temperatures will, the solubility itself already decreases, and if the phytoplankton are not producing as much, you have another further increase in oxygen, and the result is that we are seeing increasing deoxygenation taking place in the ocean, even leading to hypoxic regions and in some cases anoxic regions of the oceans. Very troubling. And they go on to open up the intro with sea surface temperatures plays a critical role in the interaction between the ocean and the atmosphere. Well, they interact there, the interface, mixing, etc. Sea surface temperature patterns drive large scale wind systems. And we'll get back to the wind systems when we talk about the mixed layer depth later on. Bjerknes, back in 1969, determined the global rainfall distribution and influenced marine ecosystems. And I've, I've done videos before featuring this gentleman's research. It's been at it for quite some time. It is therefore crucial to understand how SST will respond to greenhouse warming in terms of its mean state and seasonal cycle. The amplitude of the climatological sea surface seasonal cycle is generally larger in the extratropical ocean than in the tropical ocean, basically away from the tropical oceans. It's larger in the northern hemisphere than in the southern hemisphere. And the seasonal cycle amplitude of sea surface temperature is defined as the difference between annual max and minimum temperatures. And we can look at figure 1. Let's first go through the description and then we'll enlarge. Climatological amplitude of sea surface temperature seasonal cycle for 85 to 05, which on the left side panels, and its trend, which on the right side panel, from 1950 to 2019. And then they tell you where, which data set was used to help create these subplots. C and D, which are the right-hand panels, are based on the CMIP 8.5 pathways. For models, historical simulations are used from 1950 to 2005. And then the representative concentration pathway 8.5 goes from 06 to 19 to calculate simulated trends. Black stippling in panel C and D indicates that the trend is statistically significant at 95% confidence level on the basis of t-test. T-test is a test testing for differences in means. It's a standard statistical test. And then the ERSST stands for Extended Reconstruction of Sea Surface Temperature. Zonal average of each variable is also shown in the right side of the map. For CMIP5, multi-model mean, represented as the fixed solid line, and intermodal gray are shown. So let's take a peek at it. And why is it? There we go. Okay. Seasonal cycle amplitude from basically this, I gotta do math in my head, 20-year period. Okay. So first looking at the extended, right, the SST, and then looking at the model there. And as you can see, looking at the scale here, white, no change, all the way up to 12, 13C. And as you can see, it's most pronounced in pretty much the middle of the Pacific. Uh, it looks like in the Georges Banks region. Actually, yeah, Georges Banks region. And then, yeah, the Western Pacific is really quite hot. And then we see similar warming trends across the southern Pacific, Atlantic, and Indian Oceans. When you look at the CMIP 5, okay, we see pretty much similar results. Look at the trend here. Now, the trend is in degrees C per 70 years, and it goes from minus 1.05, 1.7, all the way up to about positive 1.7, where the darkest colors. And as you can see, where we see perhaps cooling down is the Southern Ocean right off the near the Antarctic continent. In fact, it almost looks like it's in the Antarctic circumpolar current. But the rest of the oceans are showing a warming trend, or basically the difference between the max and the min is most pronounced. Right? That's what we're talking about. The amplification, the difference between max and min, we're seeing that it's most pronounced, and therefore is leading to this increased warming of the oceans. So now when they look at the zonal average, and you can see that approximately about 40 degrees north latitude, where the zonal average is where it's greatest in the northern hemisphere, for the difference here. And then about 30 degrees south in the southern hemisphere. And it seems to be least the closer you get towards Antarctica. Right here around zero, very little changing there, and that's of course is the equator. Now, when they constructed the similar zonal average using the CMIP5 model, you can see now, you see this gray area in here? Let me perhaps enlarge this. Yeah. Okay. This is the 95% confidence interval that they placed around it. And as you can see, you get the most variability at these latitudes. And that's probably that 30 plus or minus 20%. And we see similar results here when we're looking at the overall trend, which shows that increasing difference between max and min. And notice now there's a little bit of a shift to subpolar waters, where we see the greatest trend. And you see up here, what is that telling you? Now that makes sense if you think about, that this region, the polar region, gets a lot of heat in the summertime because, near 24 hours of daylight and all that heat energy in there. So yes, you would expect to see the greatest difference between max and min, but also the fact that the oceans are warming up there. We have the influx through the Barents and the influx through the Fram, all contributing to warming up the ocean, especially the Arctic Ocean, and we're seeing the greatest difference between max min. This is where we've seen the greatest amplification. It makes sense when you think about it. But this will lead, as the authors describe, to a shoaling of the mixed layer depth. And we see similar results using the CMIP5 model. So these figures here tell us that the difference between a max and a min, the amplification, is increasing. That is the trend, and this means that the oceans are warming, especially in the upper layers. Basically, how you can distill that down. Now, they mention here that according to recent observational analyses, annual mean global SST has increased by about 0.11, 0.09 to 0.13 degrees C per decade since 1970. May not sound like a lot, but this is water, right? Specific heat of water per decade since 1970. Okay, so you got the 70s, the 80s, the 90s, the O's, and the 10s. That's 5 decades. If you wanted to simplify this and assume linear, which we know is not correct, that means on average, sea surface temperatures has increased by half a degree C. We know it's warmer than that because of the exponentiation. That's just to drive home the concept behind it. And they say different versions of the CMIP models. This trend will continue as more greenhouse gases are tossed out there. Then here comes the important bit. The CMIP5 models also simulate a robust decrease of the mixed layer depth by about 10 to 15 meters, and they reference figure 2C, which is this guy here. So let's look at figure 2. Multi-model mean, which is the line, and intermodal spread, which is the shading for panel A, C, annual mean, panel B, D, seasonal cycle, amplitudes of spatial mean sea surface temperatures. So SST on the left side, mixed layer depth on the right side. They tell us that represented concentration pathway 4.5 and 8.5 are used. The amplitude of seasonal cycle is calculated by subtracting the min from the corresponding max every year, and then the intermodal spread is obtained from one standard deviation against the multi-model mean. And one standard deviation is basically 68% of your data. Two standard deviation include about 95% of your data. So I find that a little interesting that they went with that. So let's take a look. Okay, here we go. So here's a sea surface temperature on this side here, and they're going back for is that like 1850 or so, and they project it out to 2100. Now the blue is the 4.5. The red is the 8.5. See, the red fits more of an exponential function. That's the correct one. Now, you see the different color shading that correspond to the different modeling here. So this pink is the one standard deviation around the 8.5. This light blue around the 4.5. And then I guess the dark blue, the little overlap here around the historical. But what do we see? Sea surface temperature is going to increase. Can't say that's much of a surprise. And if we look at the amplitude, so this is just sea surface temperature. We look at the amplitude, the difference between a max and a min, and what do we see? Again, an exponential increase when looking at the 8.5. 4.5, no, that's not realistic. I'll just state that right now. Got a little wider error around there, which reflects the high percentage change that they estimated, 30 plus minus 20. And these little squiggles here represent the seasonal aspects. Now let's look at the mixed layer depth, MLD, mixed layer depth, annual mean. It almost flat lines with the 4.5, but look at the 8.5. It continues to steadily decrease. So we're going from about 100 down to about, that looks like 80 or so. What that means is instead of the mixed layer depth being 100 meters, it's now 80 meters. Then when you look at the amplitude, okay, we can see again a steady decline of about, it's like from about 145 or so to about 115 or so, something like that. But the mixed layer depth is getting shallower. It's shoaling. And I'll have more to say about that later. So that's what figure 2 is all about. And, they go through a whole pile of discussions here. As I said, if you're interested, click on the URL and have at it. And they discuss how they did the models and the budget analysis. They say, here's the mathematical section. What I will say here is that this is a total derivative. So they're looking at the change in temperature with respect to time. Q is we use capital Q for heat. This is rho, so that's seawater density. That's C sub P is specific heat, and H is the mixed layer depth. Now, what's in the parentheses is very interesting. These little backward-looking sixes, this tells us the partial derivatives. So let's look at this first term, U times dt dx. So this is the change in temperature over the change in a zonal distance, in other words, along a latitude, times whatever the velocity speed is. Similarly, v dt dy is the change in temperature over a meridional line, times the velocity in that direction. W dt dz is the change in temperature over vertical distance, times again the velocity in that direction. So basically, the reason why these are partial derivative is that temperature changes are dependent on x, y, z, the changes in each one of those directions. And the UVW simply are the velocities that are associated with these changes. Now, they could have written a gradient T here. The gradient symbol is a triangle with the pointed end down and wrote capital T, and that's the shorthand way of doing. So they could have just put that in there. Q divided by rho times specific heat times the mixed layer depth minus the gradient of temperature plus a residual. They could have written it that way. That's fine. But they go on to basically say, oh, we can do a whole bunch of assumption, and we can simplify that the change in temperature is proportional to the heat divided by these terms. And then they get into a whole bunch of really fun stuff here. And they use a Taylor series expansion. Okay. Series is an important tool in calculus because oftentimes, let's say you're integrating a function and it's non-elementary. In other words, standard basic analytical methods do not work. So for example, if I'm integrating k times e to the x, that's an easy integration done by analytical methods. You simply adjust the integrand if need be, and off you go. If I'm integrating, say, x times e to the x, okay, a little tougher, but you can use integration by parts, and it's involves a little more work, but it's straightforward. It can be done. But if I have integrate e to the x divided by x, that's non-elementary. You can't integrate that by analytical methods. So you use a series expansion. Notice you can write out functions using series expansion, and you write them in the form of polynomials. And integrating polynomials term by term is very simple. And that's what they're doing. They're basically just writing these things out uh, term by term. But you can see, a whole bunch of Q's in here, so it's all heat fluxes. The bar over means that the mean heat flux there. So when you're looking at things, here's one. Take a look at this one here. E bloody ha. But there's no integrations in here. Well, they've done it for you with the Taylor expansion. But this is just a plug and chug. You get the values of plug and chug. Really, it's not difficult. Looks intimidating, but it's not difficult. I used to tell my students, do not confuse or conflate with what's tedious with what's difficult. Tedious just means a pain in the ass. Difficult means it's freaking difficult. you know, like solving second order nonlinear partial differential equations. That is, not to put too fine a point on it, a bitch to do. And I've had my experience, my share of doing such things. So, anyway, so yeah, they developed the math here, and all this is to calculate the heat budget, to calculate heat fluxes, heat advection. Okay? To go back up to this up here, well, where's that? Yeah, these are advections. You're moving from one location to another. Here along a latitudinal band, here across, basically following a longitudinal line, and then vertical. These are advections. That's all that is. Then when you go from the water to the atmosphere, that's a flux. And technically, advections are also fluxes, even if it stays in the water. Remember, a flux is some sort of a concentration for some sort of, it could be, uh, some sort of unit area, unit volume, and then that's per time. So you might see, the number of milligrams per, cubic meter per year. That's a flux. So they go through an extensive discussion of, analyzing this change of amplitude of seasonal sea surface temperature cycles. They've mentioned it's spatially non-uniform. That's to be expected. Figure 3 shows the change in the amplitude during the 21 years of basically the last 2 decades of this century relative to 21 years of 85 to '05. And so let's take a look at that. Again, let's look at the description. Projected future change in the amplitude of sea surface temperature seasonal cycle during the end of the 21st century relative to the recent past, obtained by looking at models. Multi-model mean, thick solid line, intermodal spread, gray shading of zonal mean of the amplitude is shown on the right-hand side. Excuse me. That's B and E. And that's not B and E shows the change in annual mean and the amplitude. So let's take a look at this. Okay, might increase there we go. So seasonal cycle amplitude, looking at the 8.5, and again, we see the greatest changes in the subpolar polar waters, right up here. Now notice how it is less under the 4.5 modeling. We can see that, right? You can see that right here. You want to look at the 8.5. If you're ever looking at other papers, don't even bother the 4.5. Look at RCP 8.5. That's assuming worst case scenario, which is exponentiating, which is what is actually taking place. The change in annual mean delta Q. Now, there's a change in heat, and then the change in amplitude of the seasonal del QA. And basically, we're seeing what? Look at this here, right in the North Atlantic is where we're seeing, and it's calculated in watts per square meter. That's telling us what the North Atlantic is going to warm up the most. And we see slight cooling down in the polar region. Now, why is that? Well, we're losing the sea ice. So now what happens is that heat just blasts right through the water. It fluxes to the atmosphere, leaving the water a little cooler. Now, as the atmosphere gets warmer, because there's no ice to entrain the heat content, and with supplying warm water into the Arctic Ocean, that heat fluxes to the atmosphere. It's kind of the reason why the Arctic is warming like 3-4 times faster than the rest of the planet. Remember, okay, we're looking at the water, the change in the heat in the water. So the water is giving off its heat to the atmosphere. It's going to be cooled down. But now when you look at the change in this, when you look at the seasonality, then we see here's that great difference in the seasonality. Notice this is reflecting during the summer months, or when there's no sea ice, all the heat that's being blasted in the atmosphere. This is the for the mean. So in other words, this then takes into account when you do have the ice that finally forms, and will temper it down. And then we see what? The North Atlantic is cooling. So when you look at the annual versus the seasonality, these graphs are almost flip-flops of each other. Now the change in the delta, this is the change in the mixed layer depth. Okay. So this is a loss of the mixed layer depth. This is an increase of mixed layer depth. In other words, this gets deeper, this gets shallower. So the blue is shallower, the red, brown, whatever, is deeper. And as you can see, North Atlantic gets shallower. It gets shallower in the Southern Ocean, shallower in the Southern Indian Ocean. That's for the annual. When you look at the amplitude, then we see some really interesting results. We see a lot of shoaling mixed layer depth on a seasonal basis. And that means what? The mixed layer depth is shallower, not as deep as before. In this case, it could be changed by as much as 80 meters. Look at the North Atlantic. Look into the Barents Sea. Look over here on the Western Pacific, and then the Southern Indian Ocean. In other words, mixed layer depth gets shallower. So they're basically showing that the oceans are warming, it's leading to increased stratification. The mixed layer depth is getting shallower. Now, what's the importance of the mixed layer depth? Mixed layer depth is basically reflecting wind activity. Wind blows across the water. When it does so, it imparts a stress to the surface, and the surface then churns a bit, so you get mixing. And how far down the wind effects is your mixed layer depth. So if the wind blows across steadily, and you get this additive mixing, you can get that the mix layer depth is could be down to 100 meters. In other words, if you were to drop a vertical instrument through like a CTD, you're going to have pretty much uniform values in temperature, salinity, density throughout the mixed layer depth. Then you get out of the mixed layer depth and you probably start seeing some changes. Now, of course, the mixed layer depth changes seasonally. Summertime would be different than wintertime, and so on. And that's kind of what they're telling us here, that this is changing, that the changes in the sea surface temperature is also being seasonal, but we're seeing a greater disparity in the seasonal changes, those are increasing because of the stratification, and that stratification is tied into the mixed layer depth becoming shallower. So it almost sounds like circular reasoning, but they're tied together. You have the stratification leading to shoaling, leading to the greater disparity in the seasonal differences of the sea surface temperature, which is reflecting the warming ocean. But here's another important thing why the mixed layer depth getting shallower is critical. Mixed layer depth, you're going to have your nutrients in there. Now, typically the phytoplanktons get entrained within the mixed layer depth. Very rarely do they move out of the mixed layer depth. So if the mixed layer depth is getting shallower, that means there's decreased volume, which means decreased potential stores of nutrients, implying decreased productivity. Couple that with the increasing stratification, where you cannot even mix in nutrients into the mixed layer depth, the photic zone, what have you, further adding to a decrease. Let's just say better, further contributing to the decrease in net productivity. So it's a double whammy there. That's why this is important. The SST seasonal cycle is projected to intensify mainly as a result of larger warming occurring during local summer as compared to winter, and that's what we're trying to show in figure 3. The largest warming occurs during August, September in North Atlantic because that's oceanic summer. North Pacific, the same time, during February, March in the South Indian Ocean because that's their summer, oceanic summer. And they go through a discussion of why the contributing factors for amplification. And they go through a lot of the math here. And so changes in the heat term, and other heat terms. What I want to do is get right to the discussion and conclusion. And if I was to do a deep dive in this, I'd be talking to you guys for 3 hours. So, what are they saying? Our study provides a comprehensive analysis of the characteristics and driving mechanisms responsible for the intensification of the seasonal cycle of SST. Globally, by the end of the 21st century, the amplitude of the SST in seasonal cycle increases by 13 plus or minus 8%, 30 plus minus 20% for the 4.5 and the 8.5 scenarios, respectively. The projected ocean warming over summertime is much stronger than winter. We demonstrate that on average, the global amplification of seasonal cycle of SST can be explained in terms of the increase in stratification that will trap the seasonal heat flux variability to a shallower layer. That just summed up all this. They do say that the decrease in the annual mean mixed layer depth plays a dominant role in intensifying the SST seasonality in most of the ocean basin, which is what I was alluding to earlier. And then they try to, understand the mechanisms for this amplification. So they looked at the surface heat flux component of the mixed layer temperature equation. It is found that the decrease in the mean mixed layer depth due to the increase in stratification is the most important contributor of the amplification of the SST seasonal cycle. The decrease in the annual mean mixed layer depth due to the increase in stratification is the most important contributor of the amplification of sea surface temp seasonal cycle. Increases in annual mean of net surface heat flux plays a secondary role just in the North Atlantic with slight compensation from the decrease in seasonal cycle amplitudes of the net surface heat flux. Okay, the intensification in the seasonal cycle of SST might have implications for future changes in the ecosystems. A seasonal cycle amplification may add to the existing stressors to ecosystems such as ocean acidification, reduced upper ocean oxygen levels. Therefore, understanding the drivers of sea surface temperature seasonal cycle intensification in response to greenhouse warming may help to better determine the productivity and distribution of marine species in the future. Overall, the literature indicates that there are four major stressors on oceanic ecosystems that contribute to decrease in biodiversity or mass extinctions of marine organisms or marine species. They are increasing stratification, decreasing a decrease in net primary productivity, increasing ocean acidification, decreasing oxygen levels. Taken individually or taken working in conjunction, those are the four major environmental factors that will lead to decrease in biodiversity, increased species extinction rates in the oceans. What humans are doing is exacerbating all of those factors. We're making things worse. Add in that the plastic pollution, add in that overfishing, and the oceans are under extreme stress. The oceans, as you've heard me say before, are dying. And then they go on to discuss some of the problems and where future research is needed. Okay, yeah. And then the acknowledgments here. So, what's the take home message as I wrap this up here for you? Um, Global warming is leading to intense stratification of the oceans. It's leading to greater differences between maximum sea surface temperature and minimum sea surface temperature. It's greater in the summertime than in the wintertime. This is leading to the mixed layer depth getting shallower, which has implications for productivity in the oceans, i.e., getting less, reduced productivity, which is reduced productivity at the primary level impacts secondary, tertiary productivity, impacts the entire food web system, leading to increased mortality that could lead to decreased biodiversity, increase in rate of species extinction. So that's the importance there. So I am seeing more and more studies basically examining the increasing strength of the stratification taking place in the ocean. I'm seeing studies that are now quantifying the decrease in oxygen, quantifying the shoaling of the CCD of the lysocline, and now we're seeing shoaling of the mixed layer depth. The studies quantifying the decrease in primary productivity. I just mentioned a decrease in oxygen level, the increase in acidity, and we're now seeing the stratification in the oceans intensifying. And it's because of what humans are doing in burning fossil fuels. Anyway, um, that's kind of the take home message from this study. As I said, look for the URL link in the comments for those who really want to pour through this in greater detail. You can do so at your convenience. I thank you for your time, and we'll talk soon.